Hello, welcome back. I'm John, old YouTuber. Let's try finish this PDF. Just finish eating French fries with ketchup, so I have to take a piece of paper. Let's try finish this CPU catcher. That's important PDF I like to read again later. But it's been so hot today in my apartment. Yes, I will go and clean this. I'll be back in 30 seconds. Yes, but it was so hot in my apartment I was to fall asleep. So I have to read it again another day. It's still very hot. Been like that 1 month. This is why I did not read all this many PDF because it's too hot every day. But I got this to buy a new external hard drive, 5000 gigabytes. Yes, it's still very hot, like 28. So let's try continue. And my back is hurting a bit, so I have to lay down my bed now because I have pain in my back. But I like to finish this. I have to adjust the camcorder a little bit because when I move around with this tripod, the camcorder is moving. Yes, let's try, but I need half a minute. I have a pain in my back a little bit. I have to lay down now. And I have a Danish video I need to put public, but I'm not getting up of my bed right now again. I need something to drink. Oh. Yes, I just eat French fries. Yes, I have to check my cell phone. 89 power. I think we can still continue. Yes, continue.
Hardware, which means that a store into an instruction closely following the store instruction will change that following instruction. Other processors like those in the Alpha and MIPS family have relied on software to keep the instruction cache coherent. Stores are not guaranteed to show up in the instruction stream until a program calls an operating system facility to ensure coherency. Tag RAM. In computer engineering, a tag RAM is used to specify which of the possible memory locations is currently stored in a CPU cache. 50, 51. For a simple, direct map design, fast SRAM can be used. Higher associative caches usually employ content addressable memory. Implementation. Cache reads are the most common CPU operation that takes more than a single cycle. Program execution time tends to be very sensitive to the latency of a level 1 data cache hit. A great deal of design effort, and often power and silicon area are expended making the caches as fast as possible. The simplest cache is a virtually indexed direct mapped cache. The virtual address is calculated with ANADA, the relevant portion of the address extracted and used to index an SRAM, which returns the loaded data. The data is byte-aligned in a byte shifter, and from there is bypassed to the next operation. There is none for any tag checking in the inner loop. In fact, The tags need not even be read later in the pipeline, but before the load instruction is retired. The tag for the loaded data must be read and checked against the virtual address to make sure there was a cache hit. On a miss, the cache is updated with the requested cache and the pipeline is restarted. An associative cache is more complicated, because some form of tag must be read to determine which entry of the cache to select. An n-way set associative level 1 cache usually reads all n possible tags and n data in parallel, and then chooses the data associated with the matching tag. Level 2 caches sometimes save power by reading the tags first, so that only one data element is read from the data SRAM.read path. For a two-way associative cache, the adjacent diagram is intended to clarify the manner in which the various fields of the address are used. Address bit 31 is most significant, bit 0 is least significant. The diagram shows the SRAMs, indexing, and multiplexing for a 4 kilobytes, two-way set associative virtually indexed and virtually tagged cache with 64-byte B lines, a 32-byte read width and 32-bit virtual address. Because the cache is 4 kilobytes and has 64 B lines, there are just 64 lines in the cache, and we read 2 at a time from a tag SRAM which has 32 rows, each with a pair of 21-bit tags. Alt-Hauphony function of virtual address bits 31 through 6 could be used to index the tag and data SRAMs. It is simplest to use the least significant bits. Similarly, because the cache is 4 kilobytes and has a 4B read path, and reads 2 ways for each access, the data SRAM is 512 rows by 8 bytes wide. A more modern cache might be 16 kilobytes, 4-way set associative, virtually indexed, virtually hinted, and physically tagged, with 32 B lines, 32-bit read width and 36-bit physical addresses. The read path recurrence for such a cache looks very similar to the path above. Instead of tags, vints are read and matched against a subset of the virtual address. Later on in the pipeline, the virtual address is translated into physical address by the TLB, and the physical tag is read, just one, as the vint supplies which way of the cache to read. Finally, the physical address is compared to the physical tag to determine if a hit has occurred. Some SPARC designs have improved the speed of their L1 caches by a few gate delays by collapsing the virtual address adder into the SRAM decoders. See some address decoder. History. The early history of cache technology is closely tied to the invention and use of virtual memory. Because of scarcity and cost of semiconductor memories, early mainframe computers in the 1960s used a complex hierarchy of physical memory, mapped onto a flat virtual memory space used by programs. The memory technologies would span semiconductor, magnetic core, drum and disk. Virtual memory seen and used by programs would be flat, and caching would be used to fetch data and instructions into the fastest memory head of processor access. Extensive studies were done to optimize the cache sizes. Optimal values were found to depend greatly on the programming language used, with ALGOL needing the smallest and Fortran and COBOL needing the largest cache sizes. In the early days of microcomputer technology, memory access was only slightly slower than register access. But since the 1980s, 52, the performance gap between processor and memory has been growing. Microprocessors have advanced much faster than memory, especially in terms of their operating frequency, so memory became a performance bottleneck. While it was technically possible to have all the main memory as fast as the CPU, a more economically viable path has been taken: use plenty of low-speed memory, but also introduce a small high-speed cache memory to alleviate the performance gap. This provided an order of magnitude more capacity for the same price with only a slightly reduced combined performance. First TLB implementations. The first documented uses of a TLB were on the GE645, 53, and the IBM 360/67, 54, both of which used an associative memory as ATLB. First instruction cache. The first documented use of an instruction cache was on the CDC 6600.55, first data cache. The first documented use of a data cache was on the IBM System /360 Model 85.56, in 68K microprocessors. The 68010, released in 1982, has a loop mode which can be considered a tiny and special KC instruction cache that accelerates loops that consist of only 2 instructions. The 68020, released in 1984, replaced that with a typical instruction cache of 256 bytes, being the first 68K series processor to feature truly on-chip cache memory. The 68030, released in 1987, is basically a 68020 core with an additional 256-byte data cache, an on-chip memory management unit, MMU, a process shrink, and added burst mode for the caches. The 68040, released in 1990, has split instruction and data caches of 4 kilobytes each. The 68060, released in 1994, has the following: 8 kilobytes data cache, 4-way associative, 8 kilobytes instruction cache, 4-way associative, 96-byte FIFO instruction buffer, 256 entry branch cache, and 64 entry address translation cache MMU buffer, 4-way associative. In x86 microprocessors. As the x86 microprocessors reached clock rates of 20 MHz and above in the 386, small amounts of fast-cook memory began to be featured in systems to improve performance. This was because the DRAM used for main memory had significant latency, up to 120 ns, as well as refresh cycles. The cache was constructed from more expensive, but significantly faster, SRAM memory cells, which at the time had latencies around 1025 ns. The early caches were external to the processor and typically located on the motherboard in the form of 8 or 9 DIP devices placed in sockets to enable the cache as an optional extra or upgrade feature. Some versions of the Intel 386 processor could support 16 to 256 kilobytes of external cache. Example of a motherboard with only 386 microprocessor, 33 MHz. 64 KB cache, 25 ns, 8 chips in the bottom left corner, 2 MB DRAM, 70 ns, 8 SIMs to the right of the cache, and a cache controller, OSTECA 38202, to the right of the processor. With the 486 processor, an 8 KB cache was integrated directly into the CPU die. This cache was termed Level 1 or L1 cache to differentiate it from the slower on-motherboard, or Level 2, L2, cache. These on-motherboard caches were much larger, with the most common size being 256 kilobytes. The popularity of on-motherboard cache continued through the Pentium MMX era, but was made obsolete by the introduction of SDRAM and the growing disparity between bus clock rates and CPU clock rates, which caused on-motherboard cache to be only slightly faster than main memory. The next development in cache implementation in the x86 microprocessors began with the Pentium Pro, which brought the secondary cache onto the same package as the microprocessor, clocked at the same frequency as the microprocessor. On motherboard caches enjoyed prolonged popularity thanks to the AMD K6-2 and AMD K6-3 processors that still used Socket 7, which was previously used by Intel with on-motherboard caches. K6-3 included 256 kilobytes on die L2 cache and took advantage of the onboard cache as a third-level cache, named L3. Motherboards with up to 2 MB of onboard cache were produced. After the Socket 7 became obsolete, On-motherboard cache disappeared from the x86 systems. The three-level caches were used again first with the introduction of multiple processor cores, where the L3 cache was added to the CPU die. It became common for the total cache sizes.
Yes, I have a Danish video. I was eating French fries. I need to put it public. Let's do it. I have to read this. This is important to understand how the CPU cache is working inside a CPU. So I have to put it public. And add it to my playlist. Find the playlists. There, then I'm kind of done for today. Put the memory card back to the camcorder. My other camcorder, my old Canon, is full of power, so I can continue to read some more later. I think I should try to get some more sleep today. But it's 7:40 p.m. Yes, I will put my alarm clock on, put the light off, and check my cell phone. Nothing there. Let's continue.
To be increasingly larger in all processor generations, and recently, as of 2011, it is not uncommon to find level 3 cache sizes often of megabytes. 57. Intel introduced a level 4 on-package cache with the Haswell microarchitecture. Crystal Wool, 28, Haswell-PUS, equipped with the GT3E variant of Intel's integrated Iris Pro graphics, effectively feature 128 megabytes of embedded DRAM, EDIM, on the same package. This L4 cache is shared dynamically between the on-die GPU and CPU, and serves as a victim cache to the CPU's L3 cache. 29, in ARM microprocessors. Apple M1 CPU has 128 or 192 kilobytes instruction L1 cache for each core, important for latency /single thread performance, depending on core type, unusually large for L1 cache of any CPU type, not just for a laptop. While the total cache memory size is not unusually large, the total is more important for throughput, for a laptop, and much larger total, for example L3 or L4, sizes are available in IBM's mainframes. Current research. Early cache designs focused entirely on the direct cost of cache and RAM and average execution speed. More recent cache designs also consider energy efficiency, fault tolerance, and other goals. 58, 59. There are several tools available to computer architects to help explore trade-offs between the cache cycle time, energy, and area. The Cacti Cache Simulator, 60, and the Simple Scalar Instruction Set Simulator are two open-source options. Multiported cache. A multiported cache is a cache which can serve more than one request at a time. When accessing a traditional cache, we normally use a single memory address, whereas in a multiported cache we may request n addresses at a time, where n is the number of ports that connected through the processor and the cache. The benefit of this is that a pipelined processor may access memory from different phases in its pipeline. Another benefit is that it allows the concept of superscalar processors through different cache levels. See also.